All right, let's dive right in. Today we're tackling a really cool concept in chemistry, chemical equilibrium. We're going to answer a pretty big question. How in the world does a chemical reaction know which direction to go to find its balance? You ever have that feeling where you're just not quite where you're supposed to be? Well, it turns out chemical reactions kind of feel the same way. When you mix a bunch of stuff together, how does the system know when to stop? It's like having a destination in mind, but needing a GPS to figure out how to get there. And that's the exact analogy we're going to use today. So what's really fascinating is what happens when you watch a reversible reaction over time. You see something kind of like this. The amount of your reactants, that's the purple line, it goes down. And the amount of your products, the red line, goes up. But then they just stop changing. They level off and become constant. That steady state, that's what we call equilibrium. Okay, so if equilibrium is the destination, how do we actually define it? Well, this brings us to our first huge idea, the equilibrium constant, which we call K. The equilibrium constant, or K, is the magic number here. It's a very specific ratio of products to reactants that a reaction is always aiming for once it has settled into its balanced state. You can think of it as the fixed, unchanging target for any given reaction, as long as the temperature stays the same. Let's really hammer this analogy home. K is that final destination address you punch into your GPS. It doesn't matter where you start your journey from, that destination is locked in. The only thing that can change that address is if you change the temperature. And here's what that address tells us. If K is a big number, greater than 1, it means your destination is a place with a ton of products. We say the reaction favors the products. But if K is a teeny tiny number, less than 1, it means the reaction barely gets going before it hits that balance, so it really favors the reactants. Okay, so we have our destination, K. But that's only half the story, right? How do we know where we are right now on our trip? For that, we need a kind of chemical GPS, and this is where the reaction quotient, or Q, comes into play. So meet the reaction quotient, Q. Now, here's the kicker. It's calculated with the exact same formula as K, products over reactants. The crucial difference, though, is that Q is a snapshot. It's that same ratio, but measured at any point in time, whether the reaction just started, is halfway done, or maybe has even gone too far. So let's be super clear. K is the fixed destination. Q is that little blinking blue dot on your phone's map. It is your current location, telling you the state of your reaction at this very second. Now, writing the expression for Q is pretty simple, but as you can see from these examples, there are a few key rules. We only include things that are gases or are dissolved in water, aqueous species. We leave pure solids and pure liquids out of the calculation entirely. Why? Well, their concentrations are so dense and stable, they're basically constant, so we just bake their effect right into the value of K. All right, we have our destination, K. We have our current location, Q. Now for the moment of truth, figuring out which way to drive. This is where we finally compare the two. It really all comes down to this one simple comparison. By putting our GPS coordinate, Q, right next to our destination, K, we instantly get our turn-by-turn directions. It tells us if we need to keep going forward, turn around and go in reverse, or just stop because, hey, we're already there. And there are only 3 ways this can go. 1, if your Q is less than K, your ratio of products is too small. You need to make more, so the reaction proceeds forward. 2, if Q is greater than K, you've overshot your goal. You have too many products. The reaction has to proceed in reverse. And 3, if Q equals K, congratulations, you've arrived. The system is perfectly at equilibrium. And here is an awesome little trick to remember this. I call it the Pac-Man rule. If you write Q on the left and K on the right, the inequality sign, the Pac-Man mouth, always eats the bigger number, and the point of the arrow literally points in the direction the reaction needs to go. So simple, but it works every time.
Theory is great, but let's see this thing in action. We're going to take a little chemical road trip with a real-world example to make this crystal clear.
Okay, so here's our reaction. We know its destination, Kc, is 0.64 at this temperature, and here are our starting conditions, the initial amounts of all 4 gases that we've just put in a flask. So the big question is, which way is this thing going to go? So first things first, we got to figure out our current location, our Q. We just plug our starting concentrations right into the expression, products over reactants. We multiply the products on top
divide by the reactants on the bottom, and we get a Q value of 0.040. And when you see it visually like this, the gap is just obvious. Our current Q is way, way down here at 0.04, while our destination K is all the way up at 0.64. We're definitely not at equilibrium yet, not even close. So, the verdict is N. Since Q is much smaller than K, the system needs to increase the number of products and use up some reactants. The only way to do that is for the reaction to proceed forward, to the right, until that Q value climbs all the way up to 0.64.
Before we wrap up, let's just go over a few essential rules of the road. These are the things you absolutely have to get right every single time to nail these problems. Here's your quick checklist. Number 1, always leave solids and pure liquids out. Number 2, the coefficients from your balanced equation, those become the exponents in your expression. Don't forget them. And number 3, just be aware if you're working with concentrations, which gives you Kc, or partial pressures, which is for Kp. And here's a little pro tip on language, just so you sound like you really know your stuff. When a reaction isn't at equilibrium yet, like our example, we say it proceeds in a certain direction. The word shift is really best reserved for when a system is already at equilibrium, and then you do something to mess it up. It's a subtle point, but an important one. So if you remember just one thing from this entire explainer, let it be this. Q is where you are. It's your current GPS coordinate. K is where you're going. It's your final destination. And comparing the two is all you need to do to figure out how to get there. And that's really it. You know, this whole idea of a dynamic balance, it's not just in chemistry. You see it in ecosystems, in economics, even in our own lives. So I'll leave you with this question to chew on. Where else do you see this constant dynamic push and pull towards some kind of equilibrium? Thanks for tuning in.